Renewable energy technologies produce sustainable and clean energy from sources such as the sun, the wind, biomass and water. By means of special equipments and systems, it is possible to produce electricity and heat virtually everywhere, even where grid and supplies are absent or difficult to realize. Renewable energy technologies have the potential to strengthen energy security, improve environmental quality and contribute to a widespread diffusion of energy availability. In this lesson we will discuss solar photovoltaic and solar thermal systems, while the next one will cover wind, hydroelectric and biomass plants. A photovoltaic plant allows for the transformation of solar radiation into electricity. The conversion takes place thanks to the so-called PV cells, made of semiconductor materials. Nowadays, the most used material for photovoltaic cells is silicon, which can be monocrystalline, polycrystalline or amorphous. In order to be protected from weather and external factors, the cells are assembled into modules. These modules are usually grouped into strings, which in turn are connected to the control and storage devices: inverter, charge regulator and batteries. Commercial modules are available with areas ranging from about 0.5 to 2 square meters and a weight of about 15 kilograms per square meter. The conversion efficiency of the cells, which means the ratio between produced electricity and incident radiation, can reach up to 20% and more. In general, the efficiency of the module, as well as of the whole plant, is lower than that of the single cells, due to the devices and systems losses. The power of a photovoltaic device, cell, module or system is expressed in watt or kilowatt peak, which represents the nominal power that the unit is capable of delivering in reference standard test conditions. To give an idea, a module of about 1.3 square meters with crystalline silicon cells is rated between 180 and 260 watts peak, according to the quality of the cells. Depending on the type of use, photovoltaic systems can be divided into two categories: standalone and grid-connected. In the former, a storage system, it has a battery, is interposed between the generator and the inverter. This stores the electricity when production exceeds consumption and makes it available when consumption exceeds production. Otherwise, when systems are connected to the grid, all the energy that is not directly used on site is fed into the grid. During periods of little or no sunlight, the grid itself integrates the user's needs. The electricity produced by a photovoltaic system during a given period can be estimated using this simplified formula, where EPV is the amount of electricity produced during the period, kilowatt-hour. PR is the performance ratio of the PV system. The average value is usually in the range 0.75–0.8. ppV is the nominal power of the PV system, kilowatt peak, and S is the solar irradiation incident on the module surface during the period, kilowatt-hour per square meter. The productivity of a photovoltaic system is highly dependent on the climatic context in which it is located. As an indicative figure, in AIC, a 1 kilowatt peak photovoltaic system, which means about 7 square meters of modules, can produce between 1,500 and 1,650 kilowatt-hour electricity annually, depending on the site of installation and thus on the amount of available solar radiation. Architectural integration represents an interesting opportunity for photovoltaics, since the installation of the modules on the building envelope provides a variety of advantages, such as the use of the land surface already occupied by buildings, the savings on support structures, the replacement of materials and components such as traditional roof elements, and the possibility of using the energy produced on site. In order to obtain the best performance of a photovoltaic system, whether integrated into the building envelope or not, careful planning is necessary. For example, it is important to avoid shading and overheating of the modules in order to maximize their performance. Solar thermal systems convert solar radiation directly into heat. Their use is compatible with all the applications that require thermal energy at a relatively low temperature, such as the production of hot water, but also air conditioning. Solar energy is captured and converted into thermal energy through solar collectors. The market offers three types of products: flat plate, evacuated and unglazed solar collectors. The choice of the most suitable technology among these depends on the final use, mainly on the temperature they should work at and on the mean external weather conditions. The flat collectors are quite simple. An absorbing plate, integrated with pipes for the heat transfer fluid, is placed into a box insulated at the back and along the sides. The absorber plate is treated and coated so as to absorb the maximum amount of incident solar radiation and to minimize the far infrared re-emission. A transparent cover located in front of the plate reduces the convective losses, and mainly the radiative ones, in the far infrared, thanks to the greenhouse effect. The evacuated collector consists of a series of evacuated glass tubes, each containing an absorber and pipes through which a heat transfer fluid flows. The vacuum reduces convection heat loss between the absorber and the glass, increasing efficiency and allowing high temperatures to be achieved. To increase the amount of solar radiation on the absorbing plate, some models of evacuated collectors are provided with a rear reflector foil, appropriately shaped. The unglazed collectors or plastic absorbers are very simple and quite inexpensive. These collectors are specially designed for low temperature applications and are made from ultraviolet resistant plastic. The heat losses are higher than in the two types mentioned above, but the good cost-benefit ratio makes them a remarkable product, especially in hot climates. The efficiency of a solar collector depends on its construction characteristics: absorption coefficient of the plate, optical transmittance of the glass and overall heat loss coefficient, but also on the operating conditions: average operating temperature, external air temperature and incident solar radiation, as well as the orientation and inclination. In general, we can say that the efficiency is very good for the evacuated collectors, good for flat collectors and satisfactory for unglazed collectors. In the EAC countries, the best performance is obtained when the collector is horizontal, as for PV panel, but to avoid the stagnation of air bubbles and dust accumulation, it is necessary to give them a little inclination. In order to allow the gradual heating of the water circulating in the collectors and make the reserves available even in case of absence of solar radiation, the collectors are connected to a storage system. The fluid in the collector loop is circulated either by gravity or by an electric pump that is activated by a control unit when the water temperature at the collector outlet is higher than that in the storage tank. Usually, modern solar thermal systems are designed to provide about 70% of the hot water demand, and an auxiliary heater provides the rest. The percentage of the demand satisfied by these collectors is called solar fraction. For a first estimate of the collector area needed, this graph can be used. The graph gives the collector area needed to produce 100 liters a day of hot water at 40 Celsius degrees, with an annual solar fraction of 0.7 as a function of the annual solar radiation incident on horizontal surface. The area needed for production of different amounts of hot water is linearly proportional. Finally, as regards the storage, the tank can be sized around 50-70 liters per square meter of collector area. It has to be noticed that solar thermal collectors can also be used for cooling. In this case, the thermal energy generated is used to feed a cooling process according to two types of systems: closed systems, where the solar system supplies hot water to an absorption chiller integrating the conventional heat source, and open systems, in which the solar system provides heat for regenerating at the second wheel, which is part of an adiabatic cooling system. As you have seen, in this lesson we have shown how it is possible to exploit the sun in order to produce electricity and heat, but also, in particular applications, for cooling purposes.